Let me do some tutorials to solve Bernoulli's differential equation. Example number 1. Y prime plus x times y equals to x times y to the 2. Solution. It's a perfect Bernoulli's differential equation. Compare it with the standard formula. You can put y prime here. P of x is x and q of x is also x. Y squared is y to the n. And the first thing that I'm going to do here to reduce the Bernoulli's differential equation into standard linear form. And what is the procedure to change it into standard linear form? There is a procedure, just follow that. Divide both sides by y to the 2 to have y to the minus 2 times y prime plus x times y to the minus 1 equals to x. Let's suppose y to the minus 1 equals to z. And take derivative on both sides to have z prime equals to minus y to the minus 2 times y prime. This y prime is because of the chain rule. Separate the variables to have y to the minus 2 times y prime equals to minus z prime. Replace this y to the minus 2 times y prime by minus z prime. And also y to the minus 1 by z. Multiply both sides by negative to have z prime minus x times z equals to minus x. And this is the perfect standard linear differential equation that we just got after substitution. It's a new equation. Compare it with the standard linear form. We have no issue with the derivative, and p of x is minus x, q of x is minus x. And the process under this is exactly similar that we had for a linear standard form of differential equation in the previous topic. Just follow that way. Step 2. Find the integral factor. Integral factor equals to e to the integral of p of x dx. Substitute the value of p of x, which is minus x, and integrate minus x with respect to x to have e to the minus x squared over 2. This is the integral factor that we got. Step 2. To find the general solution. Z equals to 1 over integral factor times integral of integral factor times q of x dx plus c. Substitute the value of integral factor, and which is e to the minus x squared over 2. And obviously the value of qx, which is minus x. Now I'm going to integrate e to the minus x squared over 2 times minus x dx. It's not easy to directly integrate e to the minus x squared over 2 times minus x dx. Let me do some substitutions here. Take minus x squared over 2 equals to u. Take derivative on both sides to have du equals to minus x dx. Now replace minus x squared over 2 by u and minus x dx by du. So the new equation is z equals to 1 over e to the u times integral of e to the u du plus c. Integrate e to the u. After integration I got z equals to 1 over e to the u times e to the u plus c. Integral of e to the u is e to the u. Substitute back the value of u here, which was minus x squared over 2. Push this e to the minus x squared over 2 term to denominator to have z equals to e to the plus x squared over 2 times e to the minus x squared over 2 plus c. Can I add the power x squared over 2 to minus x squared over 2? Yes, because they both have similar bases. They both have base e. After addition I got e to the 0. X squared over 2 minus x squared over 2 equals to e to the 0. The value of e to the 0 is 1. So I have z equals to 1 plus c times e to the x squared over 2. And now it is the time to finish z variable. Substitute back the value of y here for the z. If you remember, we had supposed y to the minus 1 equals to z in step 1. Now I need it back. Substitute z equals to y to the minus 1. Y to the minus 1 equals to 1 over y equals to 1 plus c. We don't need c times e to the x squared over 2. You can remove the term e to the x squared over 2 because it is an arbitrary constant. Whatever value you multiply or divide or add to the arbitrary constant. Ultimately it is an arbitrary constant and it equals to c, so we don't need e to the x square over 2 with the c. Rearrange it, so here is the final value of general solution, y equals to 1 over 1 plus c, and that's all. Well, let me do an alternate technique for step 3. Let me do an alternate method for the previous problem that I did. Example number 1. Y prime plus x times y equals to x times y to the 2. Solution. It's a Bernoulli's differential equation, and from a standard form of Bernoulli's equation, p of x is x and q of x is also x. Y to the 2 is y to the n. Change it into linear standard form. Divide both sides by y to the 2 to have y to the minus 2 times y prime plus x times y to the minus 1 equals to x. Let's suppose y to the minus 1 equals to z. Do derivative on both sides to have z prime equals to minus y to the minus 2 times y prime. This y prime is because of the chain rule. Separate the variables to have y to the minus 2 times y prime equals to minus z prime. Now replace y to the minus 2 times y prime by minus z prime, and obviously y to the minus 1 by z. Multiply both sides by negative, and now it is a perfect linear standard form. It is a new equation that we got after substitution from a standard form of linear differential equation. Here is derivative term, p of x is minus x and q of x is also minus x. Step 2, to find the integral factor. Integral factor equals to e to the integral of p of x dx. Substitute the value of p of x, which is minus x. Integrate minus x. Here is the final value for integral factor, I equals to e to the minus x square over 2. This is integral factor. Step 2, to find the general solution. The process under this is different compared to the technique that we did in the previous problem. Here I'm going to multiply the new equation z prime minus x times z equals to minus x by the integral factor e to the minus x square over 2. E to the minus x square over 2 is the integral factor. Do multiplication. I have now e to the minus x square over 2 times z equals to minus x times e to the minus x square over 2. Let me compare the left side with the product rule. We have a product rule where u times v equals to u times dv of dx plus du of dx times v. There's a product rule u times v. Compare the left side with the product rule. U is e to the minus x square over 2 times dv equals to z prime plus du of dx equals to minus x times e to the minus x square over 2 times v equals to z. This is the product rule. That's how we compare the product rule with the left side. Now can I write this term equals to the derivative of e to the minus x square over 2 times z? Yes, I can. Now take integration on both sides. After integration, I have integral of derivative of e to the minus x square over 2 times z equals to integral of minus x times e to the minus x square over 2 dx. Integration will cancel with the derivative d over dx. They will cancel each other, and I left with e to the minus x square over 2 times z equals to integral of e to the minus x square over 2 times minus x dx plus c. Again, to integrate e to the minus x square over 2, let me do some substitution. Let minus x square over 2 equals to u. Take derivative on both sides to have du equals to minus x dx. Replace minus x square over 2 by u and minus x dx by du. So the new equation is e to the minus x square over 2 times z equals to integral of e to the u du plus c. Integral of e to the u is actually e to the u. Substitute back the value of u. So I have now e to the minus x square over 2 times z equals to e to the minus x square over 2 plus c. Now divide both sides by e to the minus x square over 2. Simplify this expression to have z equals to 1 plus c times e to the x square over 2. So substitute back the value of y that we had supposed in step 1. Y to the minus 1 equals to 1 plus c. That was the value that we had supposed in step 1 to make it linear. Rearrange the term, and here is the final solution for the general solution, which is y equals to 1 over 1 plus c. And this was an alternate method for step 3. You can opt into any method, it's up to you.